Hi, in the last session, we understand the functioning of serializer module. And now in this session, we will be writing the VHDL code for this. So this is the high level of our serializer module. We have three inputs, load, din and shift enable. And we have one output, dout. This din input is a parallel data input. And this d output is a single bit output. So we will convert this parallel data into a stream of single bit. And then we will transmit each bit according to the specific baud rate. So we insert a load pulse, and when this load pulse is asserted, our shift register will capture the input data from this D input. And when this load signal is removed, our module will start shifting operation on the captured data, which is stored in this shift register. So we have this shift enable pin, and our module will shift the data every time it detects the pulse at this shift enable input. We will shift our data to the right by one position at each pulse of this shift enable input, and we will transmit the LSB of this register to the output dout. And every time it transmits a bit from the LSB, then after the transmission, this LSB data will be replaced by the next bit. And we will insert logical 1 at the MSB after each shift transmissions. And this process will repeat itself until all the parallel bits are transmitted one by one. So in our case, we have 10 bits to transmit, which include one start bit, 8-bit data width, and one stop bit. So we will need total 10 pulses. So let's write the VHDL code for this. Okay, so as usual, we will write our VHDL code on the Notepad++, and then we will simulate it on the Model Sim simulator. So for this, we will create a new file here in this Notepad++, and then we will save it as a .vsd file. So let's create a new file first. So go to File and create on New. Now save this file as .vsd. So go to File and click on Save As. So we will save this project in under the UART project folder. And here we have this source folder which we have created in the last session when we were designing our baud clock generator module. So I will select this folder. Now give it some name. So this is our serializer module. So give it the name serializer. Now select the file type. So this file is basic hardware description language. So select this basic hardware description language file. So you can see we have this baud clock generator file already listed here that we have designed in our last session. And now this file is serializer. So just click on save. Now we will write our VHDL code for this serializer module. So first we will give the library declaration. So give it library IEEE use IEEE.std_logic_1164.all. Now this is the time for entity declaration. So give it entity serializer is port and entity. Now list all the ports for this serializer here. So first we will define clock and reset signal. So give it clock. So that is input type, and this is std_logic. Now reset. So reset, that is in std_logic. Now we will declare other important input output ports for this serializer. So give it. So if you remember from our previous session, we have 3 inputs and 1 output for this serializer. So we will declare all of them one by one. So first input is shift enable, and this is std_logic type. So type shift enable, and that is input type std_logic. Next we have load input. So give it load, that is in and std_logic type. Next we have din, so that is input, and this is std_logic_vector type. Now I need to give the range for this D in input. For example, D in data or our parallel data is 8-bit wide. So the range will be 7 down to 0, right? But if we write our code like this fixed range, then this VHDL code will be very specific for this data width. And personally, I don't like this. I want this code for any bit size. So what I will do that I will create a generic for this data width, and then I will use that generic value for defining this range. So let's create the generic first. So we define the generic before this port declaration and inside this entity. So write generic. Now suppose this generic is data width. So write it data width, and that is integer type semicolon. Now I can use this data width generic here in this DN port. So what I will do that I will replace this hard coded value 7 with our generic value. So this will be data width -1 down to 0. And in the last we have output D out. So write it D out, that is output type and std underscore logic. So this is our entity part. Now let's fix the alignment for these input output ports. Okay, so now this looks better, right? So this is our entity declaration. And for this, we have defined this generic for data width, and we have defined the input output ports here. And now this is the time for architecture part. So write it architecture behave of serializer is now begin keyword, and in the last and architecture means and behave. So this is our basic architecture template. Now in this section we will declare our signals, and in this section we will define the function for this serializer module. So first we will write the functionality for this module, and then later we declare the necessary signals in the declaration section. Okay. So what we do that we will create a new process for this serializer module. So write it serializer process, and that is process. Now because this is a registered process block, so we will have clock and reset signal in the sensitivity list. So write it clock and reset. Now begin and end process. Now this is the basic template of process block. Now we will quickly write the registered process block inside this. So write it. So we have this reset condition first. So if reset is equals to 1, then do something, else if rising edge of clock, then do something and end if. So this is the basic template for our registered process block. So what we will do that we will write our functionality here in this section of rising edge of clock. So if you remember from our last session, we said that when this load signal is asserted or when this load signal is 1, then our DIN data will be captured by this serializer module. And this DIN input is actually a parallel data, or you can say that is STD logic vector signal. And this parallel data will be shifted out to the output port, that is D out. Means this serializer will convert the parallel data from D input and convert it into the series of data, and then it will pass out to the output D out. Now this is important that the data will be shifted when this shift enable pulse is given to this serializer module. So simply we will write this logic here inside this section here. So we will write a condition that if load is equals to 1, then what will happen? That our DIN input data will be captured by some internal signal or this serializer. So suppose our internal signal is shift register. So shift register will get the value of DIN, right? Now when load is deserted, then it will look for this shift enable input. So we will write else if. Now when this shift enable is asserted, or when this shift enable pulse is given to this serializer, then what will happen? Then we will shift our data that is captured by this shift register signal to the right by 1 precision. So we will write that this shift register gets the value of 1 and means concatenation with shift register. Now we will use the array attribute to define this shift register range. So this will be D in left down to 1. Now semicolon. And then we will terminate this if condition. So and if. Now there are few important things about this VHDL code. So first we will look about this 1 that we are inserting into the MSB of shift register. But before this, let's define this shift register in the declaration part of architecture. So define it. So this is a signal shift register and this is std underscore logic underscore vector, and this will having the range of d in. So we will use array attribute here. So it will be d in range, right? Now semicolon. Okay, so let's understand what is happening in this statement here, because this is our main statement of this serializer. And this statement is actually shifting the data of shift register to the right by 1 precision. Okay, so let me explain that what is happening. So consider that our D in is 4-bit wide, means it has 4 elements inside it. This means our shift register signal will also have 4 bits inside it, and the range will be 3 down to 0. So let me split this statement into individual indexes so that you can see that what actually is happening and how this statement is actually shifting the data to the right by 1 precision. So let's split this statement. Now treat these statements just like comment, and these are not part of this VHDL code. I'm writing them here just to explain this shifting operation. So as I said, this shift register is 4-bit wide, right? And the MSB is index 3. So we will have this shift register index 3. Now I will copy this. The next index will be shift register 2, then 1, then 0. So this is 2, this is 1, and this is 0. Now what I am saying that this shift register 3 will get the value of 1. So that will be our first bit, and that will pass to the highest index of this shift register, and that is 3. Next, what I am saying that this shift register 2 will get the value of shift register 3, right? And this shift register 1 will get the value of shift register 2. And this shift register 0 will get the value of shift register 1. And suppose our input value is 1010. So what will happen to this data when these 4 statements will execute for the first time? So first we will insert 1 at the beginning, and then we will get the value of shift register 3 at the second position. So it will be 1 again, because we have this 1 for this third index of shift register. Now the next value will be 0. So that will move for the first index here, and then we have this 1 at the first index. And now after shifting, that will be our index 0. So this will be 1. So this 1010 will become 1101 after this statement, right? So now the new value will be 1101. So write it 1101. Now what will happen? So first we will insert 1 at the index 3 of shift register, because we have this first value here, that is 1 at the MSB of shift register. Now the next value will be this index 3. So this is 1. So we will get 1. Now index 2. So this is our index 2 and the value is 1. So we will get 1 again. And now index 1. So this is 0. So we will get value 0 here. So this will be new data now. So that is 1110. So our new value is 1110. So when we shift this data once again to the right. So again 1 will be inserted at the MSB of shift register. Then the index 3, so the value is 1. So we will get 1 at the second position. And now the second index, so the value is again 1. So we will get 1. And now this first index, and the value is again 1. So we are getting this 1 value. Let me add one extra row here. So when I load my DIN input to the serializer, so shift register will capture the value of input DIN, right? So the input is 1010. So the shift register value will be 1010. Now if we are using the RS-232 protocol, then according to the RS-232 standard, the least significant bit or LSB is transmit first and the MSB will transmit last, right? So in this case, when the value is 1010, our LSB is 0, means this value will transmit first, then this 1 value will transmit, and then this 0 value will transmit, and in the last this MSB or value 1 will transmit, right? So now look at this 0th index of shift register. So at the first pulse, when this shift enable pulse is given, so what will happen if we can transmit this 0 which is present at the 0th index of our shift register signal when this shift enable pulse is given to this serializer module. So at the starting, we will get this 0th value at index 0 of shift register. Then at the next pulse, when we shift our data to the right by the 1 precision, we will get this 1 value. And this will be the first index of our input data, means D in input. And for the next pulse, we are getting 0 at the 0th index of shift register. And if you notice, then this value 0 actually comes from the second index of our D in input. And when the fourth pulse is given, we are getting value 1. And this value 1 is actually the third index of our input D in. Means our input data, which is a parallel data, and we can get these parallel data to the output serially if we use the index 0 of our internal signal shift register. So 0, 1, 0, 1. Now this is the reason that why we have shifted our D in input or the shift register to the right by 1 precision. Because we have to transmit index 0 or the LSB of the data first, and in the last we will send or we will transmit the most significant bit or MSB. So what we will do that we will assign our D output whatever the value we have in the shift register at the 0th index, right? So we will write the statement that D out will get the value of shift register 0. So this statement will do the same thing which I have explained to you here in this example. Now there is one important question, that why we have inserted 1 here at the starting of shift register. Why we have not inserted 0 here, and if there is any impact if we use 0 here instead 1. So the answer is definitely yes. We have used logical 1 here because we are using RS-232 protocol standards, and according to that the start bit is always logical 0, and when your RS-232 protocol is not transmitting any data, means when it is an idle state, then it will have logical high value. So if you notice at the last transmission, means when this transmission is complete and all the bits are transmitted over the RS-232 protocol, then this value will indicate that now this is an idle state. But if you force 0 value here, then after the whole transmission is complete or all the bits are transmitted, then because of this 0 value, our transmission module will read this that we are getting a next data, and that is not correct, right? So we have used this value 1 instead value 0 here because our default state is 1. Now if you are working on some different protocol that have value 0 as in default state, then you will insert 0 here. Okay, so we can do one more thing here, that we can write this code for any default value. Means if default value is 1, then it will work accordingly. And for some another protocol, if the default value is 0, then this program will work for that as well. So what I will do, that I will replace this hard-coded value 1 with some generic value. And suppose this is defined as default state. So I will replace this 1 with default state. And everything is same. So let's define this default state in the generic section. So this is our generic section. And here we will define this default state. So default state, and that is std underscore logic type, right? Okay, so let's move down and delete all the extra lines which I have used to explain you about this shifting operation, right? So let's delete these lines from here. And we have one more thing to do, that is we need to define the reset condition. So what will happen when reset is asserted, that our shift register will get the value of default value. So our default value is 1, right? So what we will do, we will use others keyword like this. All the values will be 1. So this statement will assign 1 to all the bits or all the elements of shift register despite of its range. So if it is 4 down to 0, it will assign 1 1 1 1. If shift register is having 8 elements, then it will assign value 1 to all the elements. And now because we have defined a generic for this default value, so we will replace this 1 with the default state. So replace this with default state. Okay, so now everything looks good and our code for this serializer module is completed. Let's give a quick look that everything is fine. So this is library declaration, that is good. This is entity declaration and this looks good as well. We have defined generics here and then we have defined all the input output ports here. We have clock and reset as a general structure for a registered process or as part of a synchronous system. Then for this serializer, we have this shift enable input and load input and both are std logic type. We have this din, that is input, and that is std logic vector, and the range is data width -1 down to 0, and we have one output, that is dout, and this is std logic type. And now we have this architecture section. So we have declared this signal shift register, and that is std logic vector type and having the same range as din input. So we have used array attributes here. Now begin, and we have used this serializer process. So we have this clock and reset in the sensitivity list. Now we are seeing that if reset is asserted or this reset is equals to 1, then shift register gets the value of others default state. So for this RS-232 protocol, the default state will be 1. So when this reset is high, all the elements of this shift register will get the value of 1. Now we have this else if condition. So this is the basic template of our registered process block. And inside this, we have this load condition. So when this load input is high, then our shift register will get the value of din. Means when this load pin is high, our din input will be captured into the shift register signal. And please note that the range of din and the range of shift register must be same. Now we have the second condition inside this. So when this load signal is deasserted, means when this load signal is 0, then we will check for this shift enable pulse. And when this shift enable pulse is given, then we will shift the data of shift register to the right by 1 precision. And then in the last, we will assign the 0th index of shift register to the output dout. So this is our functional description for this serializer module. So now we will open the model sim simulator and we will check this code for any syntax error. So open model sim simulator. So model sim, enter. Let's maximize this window of model sim simulator. So if you remember from the last session, when we have started working on this UART project, we have designed this baud clock generator. So this was one module of our big system or this UART project, and we have the right code for the test bench for this baud clock generator. So both of these files are listed here. Now we are working on the same project, so we will import our serializer module here in this project. So what we will do that I will right click here and you will see the option of add to project. And now I will select this existing file because we have written our VHDL code for the serializer in Notepad++ and we are just importing it into this model sim simulator. So click on this. Now browse the file. So our project is inside this UART project folder, and here we have this source folder where we have all the source file or all the VHDL file listed here. So we saved all of our source file here in this folder only. So we have written the code for this serializer this time. So select this and click on open. Now hit OK button. And now you can see that we have this serializer.vsd file listed here. And the status is question mark because we have not compiled this VHDL file yet. So first we'll compile this program. So right click and click on compile and then compile selected. So you can see the message here and it is saying that the compilation of serializer.vsd was successful. Means there is no syntax error. Okay, so now we will write the test bench for this serializer module. And then we will test it that if it is functionally correct or not. Means if it is converting the parallel data into the serial data correctly or not. And then if you are correctly getting the output at the D output, right? So in the next session, we will write the test bench VHDL code for this serializer module. So this was our VHDL code for this serializer module. And we have checked it for the syntax error as well. And our code is clean now. So in the next session, we will functionally check this module and we will write a test bench for this. And we will test that functionally our module is working correctly or not. So stay tuned for the updates. If you did not subscribe till now, then please do subscribe to learn and grow community for regular updates. If this video is informative, then please like this video, comment on video and don't forget to share. Thank you for watching.